Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So Josh Menke did his master and PhD degree at the Brigham Young University. And in his thesis, he worked on neural network models, learning neural network models, and hierarchical Bayesian models for individual players, which is what he's going to talk about today.
So I'll present some of these models that I've developed here for rating individual players. But first, I want to ask, why do we want to rank and rate, and especially in groups? And so my feelings are ranking and rating in groups in general is important, simply because most of what we do nowadays in the real world is done in groups. Just simple examples are team sports. How do you rate individual players within the teams? Another example I thought of was we could rate individual executives within executive teams and competing corporations, and then military applications. So I think even though we've done a lot of these models for gaming, I think we've kind of barely scratched the surface of what we can do in terms of rating individuals inside of groups. But so like I said, though, one of the main reasons that I started doing this was because of computer and video gaming. But computer and video gaming is a very big industry nowadays. So as an example, in the U.S., it was $18 billion of the gross output of the U.S. in 2004 came from computer and video gaming. So why would rating in gaming be important? Simply because players, one easy reason is because players prefer games that help them compare themselves. Competitive players like to be able to have bragging rights over other players. But another reason for rating and ranking games that you've probably heard of here is you can use this information to balance the teams, and that makes the games more fun. So even if you're a player that doesn't really care about your personal statistics, you do care about probably the challenge level and having fun. And having this information allows you to improve the challenge level, improve the fun factor, which is what Drs. Grappel and Grapel and Herbrick have done with TrueSkill. Another thing you can do if you model aspects of the games themselves, you can use the statistics you get out of it to improve the game, or to improve the levels in the game. And I'll talk a little bit about how some of the models that I suggest here can be used for that. But first, for a brief background in ratings, you've probably seen this already too, if you've heard about TrueSkill. But so first we have Arpad Illo, who in 1978 he suggested a model for chess, which is essentially a Thurstone Case 5 model where they give ratings to the players, and then you assume that the difference in the player ratings follows a normal distribution that allows you to predict whether or not one player will win or the other. This was later modified to use a logistic distribution instead, is more common nowadays, and I'll talk a little bit about why as well. Mark Glickman, he's one of the the big guys on the stats side that does stuff with ELO and with chess ratings. He's also contributed to this these rating systems. He used a kind of a Bradley-Terry model. He actually took the logistic version of the ELO model and showed how that really is just a Bradley-Terry model, and he extended it to include uncertainty. So you could say more than just a player has a rating. You could say a player has a rating, and we also have some level of certainty about that player's rating. And he was basing this on the number of matches that these players had played already, and also the amount of time between these matches. So that's kind of a background, a brief one on ratings in general. And now this is just for rating single players against single players, or teams taken as a whole against other teams. Whereas the models that I went on to look at rate players out of groups more than just individual groups against themselves. We want to see how the players within the groups do. And so these are just in the last year, and then for the last 2 years, because from what I understand, TrueSkill came out earlier than it was developed earlier than it was able to come out. But there's been some work done in this area. So what TrueSkill uses is a kind of a generalized Bayesian Thurstone Case 5. And so they took it, they generalized it to be able to handle individuals inside of teams, and they also used a Bayesian model. Huang just recently also, he kind of generalized the Bradley-Terry version of this model to allow for teams. He uses a pretty similar likelihood to the one that I use, and he fits his with a maximum likelihood method. He's not doing a Bayesian method there. Now, so what I've done is a hierarchical Bayesian version of the Bradley-Terry model, and I've also added some extensions that allow you to improve the predictions and also analyze the game. So a little bit more than the previous models had done. So first, what's a Bradley-Terry model? Basically, you have two opponents. They have ability parameters, say lambda 1 and lambda 2. And the probability that the first opponent wins is just his ability parameter over the sum of the kind of ability in the system. And that's how you compute the that's the likelihood there of that first player winning. The current logistic ELO uses Bradley-Terry, but instead of just taking a rating as is, you have some other player parameter, say theta here, and you exponentiate it to get the player ratings. Now, the reason why they switched kind of from the Thurstone case 5 model to the logistic model, this is kind of the rumored reason. I actually don't know the study that was done. I think it was done just among chess people that like chess. They just did a big empirical study where they looked at how the original Bradley-Terry, or the original chess ELO rating system using the normal distribution, how well that was predicting. And they found that it was a little bit more conservative than they saw in practice, that weaker chess players were more likely to beat the stronger chess players than that model was predicting. And so that's why they switched to a logistic model, which is a wider distribution and allows a little bit for more the possibility that weaker players could have a greater chance of winning. That's kind of the accepted reason why they switched. It doesn't necessarily mean that it's a better model for the games that we're looking at. That's just why one of the reasons why that happened. So now I'm going to talk about the application I applied these models to. It's called Wolfenstein Enemy Territory. What you have in this game is you have two teams or sides. You've got the Axis side and the Ally side. It's got a kind of a World War II theme to it. It's objective based, and so in the competitions, there are some objectives that either side has to accomplish in order to win the match. It's multiplayer, so the two sides are made up of several players each, and it's also online. And because of its online, it's kind of a public online nature. You basically have these servers that are hosted, and players come and connect to these servers. And one of the challenges with enemy territory and predicting is that these players are free to come and go and switch teams at will. So we don't have as much control as you do in something like Xbox Live, where you can wait for the players and then have them play. In this case, the players can even switch teams in the middle of the game and things like that. And so we have a little more complexity there that we had to deal with. Also, you also have some asymmetry in enemy territory where the number of players per side isn't necessarily even. You can have 5 players against 10 players. Also, the fairness of the maps that the players compete on, these playing fields, that's also not necessarily even. There are maps where it is easier for the Axis side to win. And so as an example, I'm sure some of you are not as familiar with enemy territory in soccer, or I guess football, as you would call it. So if you think of a football match, where you have your field and you have your players, but instead of 11 on 11, maybe it's like 13 on 9 or something. I don't know, did that add up? Yeah. And then even beyond that, let's just imagine that the soccer field or the football field is tilted. So it's on an incline, so the ball naturally rolls towards one side, so it's actually harder for that team to win. And then throw in the fact that players are free to come and go as they want. They'll run off the field and another guy will run on every now and then. Sometimes they'll switch teams. It's easy to tell what team they're on once they do switch teams, but this can happen. So then kind of imagine predicting in a situation like that. And just, for a fact, Splash Damage, the maker of the game, is located in London. So there's a concept in enemy territory that I'll refer to a little bit in these models called map side. So these matches take place on these maps, and there's an Axis side and an Ally side. So when I talk about the map side, I'm talking for a specific player I. He's always going to be playing on side S on map M. So his map side is referring to the map he's playing on and which team he's on, whether the Axis or the Allies. So now I'm going to talk a little bit about the data that I used and the models I used to fit it. So my first data set, I had 100 matches per server on 3 servers. So I followed 300 matches. That comprised about 877 players and roughly 7 matches per player in this set. And it's kind of an example of what this data looks like. You have a line that gives you information about which map is being played on, how long the match lasted in milliseconds, and then you have a line for each player in the match where you have the name of the player. You have something called a GUID, which basically uniquely identifies them as a player all over the world. And then you have how much time they spent on the Axis and Allies team. And you'll notice right here immediately that the amount of time some of these players are spending is actually less than the total time. So then they're not there for the whole game. So that's an example of how they're coming and leaving. And you notice this last player, he spent a significant amount of time on the Axis team as well as the Allies team. So that's just an example of what the data is like here.
Do they swap sides to make it fair?
Sometimes, yeah, and sometimes we force them to switch sides to make it fair. And sometimes they just swap sides. You know, it's not uncommon to see players that'll switch sides because they think their side's going to lose. Or they're not having as much fun because their side is losing really bad.
They switch sides to make it a massacre.
Right, yeah, exactly. Anything to end it quickly, I guess. So look at so I said I used hierarchical Bayesian models. So here's Bayes' law. We want to look at, so what I want to know is I want to rate these players. And so the player ratings I'm going to call theta as a vector. And so what I want to get is the probability distribution over these ratings given the matches that I observe. So by Bayes' law, this will be equal to the probability of the matches happening given these player ratings times the probability of those ratings there. So what I'm going to need over the normalization constant of the space. So what I need is I need a prior first. I need some model on the players, where I expect these player ratings to lie. And then I need a likelihood, or kind of what I use to predict the matches, the probability of each match given those parameters.
Sorry, is that the probability of a match occurring, or the probability of someone winning a match? Or?
It's the probability of the outcome of the match, that what actually happened, given the player ratings.
Right.
Yeah, over all the matches, essentially. Okay, so here's a basic player model I can start with. Let's let theta I represent player I's ability to help their side win a match. So one simple model we could use for theta I is just that it's normally distributed. Has some mean mu, some standard deviation, sigma squared naught. That's one way to look at a player's rating. We can let mu equal 0 without loss of generality because in enemy territory and rating there's no standard. So in chess it's common to see ratings between like 1500, 3000, that area. There is no standard for enemy territory, so I can easily just simplify and say we'll just let mu be 0. So I said it was hierarchical, so I'm going to give a prior distribution to sigma squared naught that I'll talk about in a minute, instead of assigning it a value as a prior. And so what you end up with is a distribution that's symmetric about 0. The good players are positive, the bad players are negative. Just kind of a normal distribution there. But probably something kind of naive about this model is, so I mentioned there's that map side effect, that maps can be unfair depending on which side you play on. So this doesn't take that into account, but in enemy territory that's something that's in the game by design. And so if you don't take that into account, you're probably going to be, you're going to make some mistakes in your prediction. So we'd like to account for this. So like I said, the map fairness varies. And so one question is this map fairness, is that uniform for all players? Does it affect different players differently? Is there some interaction between players and maps? And so I'm making the assumption, based on my knowledge of the game design, that usually this is going to be uniform. That if it's harder for the Axis team, it's going to be just about as hard for everybody on the Axis team. So this is what I did to model that. I said instead of just having theta I have this theta I ms, which basically says player I's ability to help side S win on the map M. And one model that we could use for this, the model I'm using, is just an additive model, where I say player has his base rating, which is theta I, and then you add to that a gamma ms, some other a rating for that map side. And again, I'm going to put another prior distribution on the gammas there. So yeah, so your rating as a player, you have some rating, and then depending on how hard the map is for what side you're playing on, that's going to go up or down a little bit. Now this is similar to what Agresti did for a home field advantage parameter for normal sports, except instead of having just one parameter like he does for the field, I have one for Axis and one for allies. It's just a model decision. I could have just chosen we're going to have the allies parameter, and then if you're on the allies team, that affects you. This is just how I did it. It doesn't make a lot of difference as far as the results that I got, because I tried both ways. And this is just the original choice I made for simplicity. Something interesting, though, about having a map side effect is it means now a more skilled team could actually play a team that's not as good, as long as they play on the more difficult side for the map. And that's something interesting actually in enemy territory. We have these maps that are not balanced, but the more skilled teams can still have a fun time because they're playing against, not as good team, but they're playing on the harder side to win. And then we actually see some evidence of that in the teams that the players that are better choose to play on, the sides they choose to play on. Also, it lets you judge which maps are more balanced. This can be used by the people that decide which maps are going to be played on a specific server. They can choose maps that are more or less balanced. And it can also be used for map designers. They could look at the statistics and say, you know what, this map we've made, it's a little bit uneven on the ally side. We're going to make some changes to the structure of the map, to the goals in the map, to make it more balanced. Or less balanced if they want to. Okay, so now I mentioned that the enemy territory, you've got public servers all over the world that people host for fun. And so it would be nice if we could compare players across all of these servers and rank them in some global way. And so to kind of decide how a specific server affects a player's rating, because different servers have different settings, different maps, different players, I decided to add another kind of server bias I called psi there. And I added the same way I did the map bias, just another additive effect. So now a player's rating is determined not only by what map inside they play on, but also offset by kind of the server difficulty. And you'll probably notice that I'm modeling this as an increase in the rating, so it's not really server difficulty, it's server easiness, but server difficulty sounds better. Just remember that lower, not higher values of psi mean a more difficult server. And so it's like I said, now it's composed of these three effects. So some interesting things you can do with this value is, well, you can use psi to choose which server you play on. You can pick servers that are easier. You can rank, like I said, you can rank players across the servers. This does require some server crossover. It doesn't mean that players have to play on 2 different servers in order to compare them, but somehow in the combination of how they play around all the different servers, there needs to be enough crossover where you can compare 2 servers. It's kind of the idea. If a whole bunch of players only played on one server ever and no one else left that server, it wouldn't be fair to compare them to other servers.
Excuse me, I've just lost track slightly. Is theta just a sort of pure rank, or does it have some relation to the probability of winning?
Yeah, it does. So the probability of winning, I'll show in a second, is going to be proportional. Actually, it's on the next slide. So here's that theta there. Yeah. So we choose a site S's probability of winning proportional to e to the. So what this is here, this is the sum of all the players on the team. So kind of like TrueSkill, the way that I construct a team's strength versus just a single player's is to exponentiate the sum of that team's skill. And so this value here is after already summing up the player's map and server effects, and I add them all together to get a team skill. And that's something that's nice about exponentiating this for types of games like Enemy Territory and and also similar games that use TrueSkill for. If you have an uneven number of players per team, it makes the effect of having more players exponential, which makes sense to me in a real-time environment, because in chess, if it's like 2-on-1, that's not as big a deal because those 2 players can't make 2 moves for every chess move. But if you have more players in a real-life situation, you have more players. So you have 10-on-5, those 10 players are all moving simultaneously. And this results in an exponential increase in the skill in those situations, which is nice. Versus if I had not exponentiated the player ratings like this.
Is there any difference between m-s and m-s? Does it mean anything?
Where is that? Do I have that in here?
m-s you've got on the right there.
Oh, so that's not supposed to be a minus. It's supposed to be just m-s. It's
the m-s.
It's the map side combination there. It just means well, it's not. So it could kind of be a comma s. It could be m comma s, but it's just that the way that I model that gamma parameter is per map side. So I mean, I could do kind of m comma s. That's just how I chose to write it there, I guess. It represents the rating on that maps for players that play on that map side, on the ally side, on some map m, or the axis side. So now the way we use this then to predict is take the team scores and just use classic Recursive model. Just the probability of the axis team being the allies team is going to be score for the axis over the axis plus the allies. And so now we can look at kind of all the equations that go into the likelihood function. This is just the same thing, just that I've written out so you can see that it's a product over all of the matches. So the likelihood is a product over all the matches of how likely each of those matches were. So now there's a problem with this though. So like I talked about in these public servers, players come and go and they change teams, and so we need to take into account how long they're playing per team. And fortunately, this is available in the original data. And so to handle this, I kind of use just a simple exposure model where instead of just summing the team strengths of all the player strengths to get a team strength, I do a weighted sum. And so I weight each player's contribution based on the % time that he played. And so that's what that tau is doing there. It's just weighting each of these players by how long they played. And something interesting about this is if you sum up the taus for each team, you get the the effective number of players per team. But anyway. So now let's talk about how I selected those prior. So it's a hierarchical Bayesian model. instead of choosing non-informative priors, we have these hyperprior distributions. And so what I did was I put the common kind of normal inverse gamma situation here. So these are inverse gamma distributions. And I chose the alpha and beta in these distributions so that the means would be around 1 and the variance around 1/3. And all this really does is it keeps the player ratings within about -3 and 3. The main reason for using hyperpriors is just so I don't have to choose them myself, and I can still retain any kind of relative differences between them on fitting the model. It gives me a little more flexibility that way. Okay, so that when I say fit with MCMC quickly, I don't mean that you can fit quickly with MCMC. I'm just saying that I'm not going to go really deep into Markov-Chain Monte Carlo. The basic idea is I can sample from the player ratings. It's a nice algorithm that lets you sample from each of these individual ratings and generate a lot of samples for each parameter. And so if I want to find the mean of a player's rating, I just take the mean of the samples. If I want the standard deviation, I just take the standard deviation of the samples. That's just MCMC there in a nutshell. And these are kind of the results I see. Of course, these players' names aren't going to mean anything to you, but this is just to give you a feel for the type of results. We have the posterior mean there, and I'm ranking them kind of similar to what they did with TrueSkill. I'm ranking them 2 standard deviations below their means. If I have time, I'll show you another way you can rank players. But this is now something interesting here that you'd hope to see in a ranking system like this. Is you see the 3rd place person, he's played 9 games and he's gone 8-1, versus the 8th place person who's gone 9-0. And so you say, why is the guy with the undefeated record ranked lower? And so hopefully that's because the guy with the 8-1 record is playing games that are more difficult, or he's losing games that are more difficult. Whereas the 9-0 guy, he might have played easier games. They're obviously both good players. It's just something you'd hope to see. Now, something interesting is because I fit that server difficulty parameter, I can list how difficult these servers are and rank them by that. So here we see, perhaps if you want a more challenging game, you want to play on server 2. Whereas if you're a newer player, you might want to rather play on server 1. And this is that's all. So now also we fit those map side effects, and so just to show you an example, so those are some map names, Oasis and Venice. We can look at these maps now and see how fair they look. So here we have Oasis, which is looking kind of a little bit unfair for the allies, whereas Venice is looking more fair. Something that's interesting is that these are both popular maps, despite how unfair Oasis is. And this is, I think, largely because on Oasis, the good players often will play on the harder side. And so this is a map that allows really good players to come play against not so good players, but still have a good challenge level.
Can I ask you a question?
So for a given map, the bias for allies is not inversely proportional to the bias for the axis.
Yeah, so that is kind of odd there, isn't it? So the reason this happens is because I'm modeling them separately. Yeah. And also because you can have an uneven number of players per side. So in the end, if I could model this as one parameter, actually, and then you'd have just 59 or something.
Just to get a feeling for how hard this inference problem is the true posterior log concave of your model?
Oh, is the likelihood concave? Is that what you're asking?
Posterior distribution that you're sampling from.
So if I understand what you're asking, so just last ICML, Huang uses a similar likelihood that I do, and he showed that it was the same likelihood as a kind of the max entropy crowd uses, and that it's known to have a global minimum. So that it is. I think it's.
It's more about the multimodality rather than.
So whether players can have.
Are there multiple explanations for the data? That's really what I'm.
Oh, okay. So are you saying that? Yeah. So it's.
I mean, presumably if there's some redundancy there is, if you've got 2 players who always played together, you don't know whether there was a skillful one and a bad one or 2 middle ones. But I mean, aside from that, are there other forms of multimodality in the posterior?
So yeah, in a system like this, I haven't seen a lot of evidence of that yet. I know it is pretty complex, but I mean, you could have situations like you said where if 2 players play together a lot, it's hard to tell which one of them is really better. and the hope is that you play enough games and you find that out whether or not that's true. And also there are other effects going on in the same vein where you could have two players that when they play separate they're so-so, but when they play together they both play exceptionally well just because something about them, the two playing together causes they like to play together, or they're really good at coordinating together. And those type of effects I'm not modeling here yet. And that,
you seem to have a fairly simple model, and you've chosen conjugate priors, and it's not a complex model. I wonder, can you show analytically that it's
that there's
non-concave posterior?
Oh, I don't know that. If I can show if that would be a good thing to look at. So instead of just running the empirical results, see if I can prove that the so I do have some theoretical. So there's some results based on some theory about how I can look at it from a. It's still using empirical data, but it's kind of more of a theoretical, statistical way to judge how good the models are, and I'll talk about that in just a minute. But yeah, I haven't tried to analytically look at whether or not I have that case.
Question?
Huh?
The standard deviations here seem awfully high if you're making conclusions about this.
Yeah, so this is a small data set, right? So even that's a good point. Even though these are, if we were to look at these distributions, they're close enough to where you think the allies have some advantage, but you might not believe that that's going to happen all the time.
Hang on, you said you over-parameterized the model, didn't you? You said your map effect, you have an axis thing and an allies thing, and those could both go up by 3 or down by 3, and it would be exactly the same predicted distribution. So you expect the error bars to be huge. It's the difference you should be looking at.
Yeah, so here
to actually see what the error bars really are.
Right, and so I thought of that after I ran these, and I have since run results where I just use one parameter for both, and the overall results didn't lead to like an increase in accuracy or anything like that, but it does lead to some parsimony. But yeah, it's true. It is over parameterized. Those are very those two variables are very correlated. There, both of those ratings.
So the marginal error bars are huge, but it doesn't matter. There's nothing wrong with the model. It's perfectly reasonable.
Yeah. So, and I think a lot of the variation in this also just comes from the data set's pretty small still. And there really is a lot of variance in these maps too, more than. There's still a little bit more variance than I'm able to always explain just because of the dynamic nature of the game. So here's something interesting. Val Johnson in 2004 in Annals of Statistics, he proposed a Bayesian chi-square goodness of fit test. So he kind of proved that there's a way to get p-values out of each joint MCMC sample. And the reason I did this is because at the time, and I didn't have any methods to compare this to. And it never sounds good to say, just trust me, it works well. So what this does is it actually allows me to judge how good the model is without having another model to compare to yet. And so what I have here then is basically the mean p-value for each of these servers based on his chi-squared goodness of fit test. And then when I say all, I'm meaning I'm fitting all servers together using the server parameter there. So we see for the most part, so you want a p-value to be kind of below 0.1, below 0.05. So for the most part, servers 1, 3, and then the combined case looks like we've got some evidence that the models are fitting well. Whereas for the second server, we're not so sure if the model did as well there. And it's actually true that server 2 does have a less consistent player base. It's kind of known to be kind of the beginner server. There's a lot more turnaround, a lot more different kind of variance in the players that come and play there. And also of interest, the biased accuracy of these models is near 100% in how it predicts. And I say biased because I'm saying I fit the model using all the data and then I predict. So it's not really a fair assessment of the accuracy, but it is interesting to know that if you overfit it, it can predict pretty well, despite it being a pretty simple model. But there are some problems fitting with MCMC. Basically, the main problem is that the average enemy territory match lasts 15 minutes. Fitting these 300 matches takes 30 minutes with MCMC. And if you're going to keep adding matches and refitting every time you add a match, MCMC won't be able to keep up with new matches. So if you want to give players real-time ratings, essentially you can't use MCMC. The same problem that I'm sure you run into with using expectation propagation and with TrueSkill. So with yeah, it's a little bit faster than MCMC, right? So in the second data set here, I have 5,000 matches now. I've got over 2,000 players, and so if I wanted to fit this with MCMC, it would take on the order of days. So some common efficient solutions are pretty common on the statistics side of things, the Newton-Raphson method. There's kind of the ELO, Glickman, that kind of what they did with their updates for chess, and then the expectation propagation. And so I was on the standard stat side of things when I developed these methods, so I chose Newton-Raphson. So just to review this, those of you who are familiar with neural networks will kind of recognize this. It's very similar to the standard batch neural network training, where you do include the second order information. You basically look at your parameters, you take the first derivative of your parameters with respect to your loss function, and the matrix of partial second derivatives, and you iterate over all of the data. And so each k is one iteration over all of your data. And something interesting to note, the negative inverse of that the negative inverse of that matrix of partial second derivatives is the covariance matrix of the multivariate normal approximation to the data. So what that means is I can now get variance on the players and covariance, but I can look at my certainty in the players' ratings by looking at that quantity there. But there's some problems with this as well. If I wanted to use this method, I would have to store match histories and then refit the data after every match. And so this is going to eventually become impractical and slow. It'd be better to be able to just do a single update and not worry about the history of the matches. Another separate problem is just that matrix of partial second derivatives is going to explode. With millions of players, you can't even store it nowadays. And not to mention that it takes too long to invert. And so now I turned to something I'm calling recursive Newton-Raphson. I call it that just because that's what on the statistics side they would probably call it, versus on the neural network side or machine learning side you might call it more of a kind of incremental Newton-Raphson method, online Newton-Raphson method. So basically, just a couple years ago, Batu and LeCun came up with a way of doing what they were out to do is just kind of prove that it's more efficient to train using kind of online incremental for neural networks learning versus training in batch mode. And so it's very similar to the Newton-Raphson method, but instead of having that matrix of partial second derivatives, you have a leaky approximation to it, kind of a running average. And what I mean by leaky is the fact that you're losing information as you go. You're letting it kind of leak. Because to construct that, you're taking a weighted average there of what you currently have as the approximation and the newest approximation of it. So I kind of adapted that to what I was doing. Just as a side note, they did some empirical and theoretical justification to show that this would asymptotically outperform Newton-Raphson, and they also made the claim that it would asymptotically outperform any batch or gradient descent.
Sorry, on the previous slide, could you just give us an intuition as to what the size of these vectors and things are? So theta t is a vector.
Yeah, so theta t, sorry, that's basically all the parameters of your model. It's going to be the player ratings, the map ratings, the server ratings in my case. And and so phi t is going to be a matrix that's the same size as theta by theta. That
Hang on, isn't it the case that you only need to have storage equal to a vector for phi?
No,
it's diagonal.
Oh, right. I didn't mention that. I'm sorry. So you could do it without diagonalizing it, right? And then you'd save all that covariance information. But yeah, I diagonalize that because it takes too long to store. So basically, instead of storing how a player reacts with all other players, I'm only looking at how just the variance of a single player with himself. And so I diagonalize that matrix. Thank you. Sorry about that. Okay, so this is how I applied it. So I derived the log posterior, and then now instead of using hyperpriors like I did with MCMC, I took the priors from MCMC that I'd already derived for these for the standard deviations, and I just plugged them in. And I'll tell you a little bit why I did that. But so here's kind of what a player rating update looks like, or the first derivative. Sorry. So basically what we have here is the winning time, how much percent of the time this player spent on the winning team, minus it's essentially the prediction for the match, and then minus a Bayesian shrinkage parameter. And now the very last term is the one that's a little bit tricky using this kind of recursive Newton-Raphson method. That the Bayesian shrinkage parameter basically is what shrinks the ratings kind of back towards the mean. But when you're doing it in a batch mode with standard Newton-Raphson method, or statisticians are called iterative mode, which gets confusing because neural network guys sometimes use iterative and incremental interchangeably. But so if you're using it in batch mode, you're going to apply that shrinkage once over all of your data. But if you're doing this kind of recursive incremental, you need to you're applying that sum part of it once for every update. And so you need to have a way to apply what is usually applied over all your data a little bit at a time. And so there's a couple ways you could do this. One way is just to figure out how many matches that player is going to play and just divide each update by that amount. But you really don't know that beforehand, how many matches a given player is going to play. And so what I chose to do instead is to weight each by that infinite geometric series. And so the series, it sums to 1, so it's kind of like applying it once. And it's also kind of nice in a Bayesian sense because it basically means the effect of the prior is going to diminish over time and be swamped by the data. Some nice things you get for free when you use these recursive algorithms is you can track time-varying differences. Each update is basically a weighted sum of prior knowledge with new knowledge. And so if you have a player who is getting better over time, it'll naturally track that for you. Also, because the variance approximation is leaky, you can also track changes in the variance over time. And so in this, I see players, as I monitor the system, that they'll kind of quickly converge to their rating, and then they'll get better or they'll start playing erratically. Their variance will go up, and their rating will change faster back to where it should be now. So here's some results with using this method. These are the accuracies I got. These are measured before updating for each match. So I predict the match's outcome, then I update. And so they're not biased by that match. And so I'm sitting around 69, 72%. And so you ask, how good is that? Because usually that doesn't sound that great. And so I put an unfair comparison here. Not that I'm really saying this is any better than TrueSkill, but the TrueSkill reported around 62% on large teams. And this is more just to show 70% might be pretty good comparatively. It's not fair. I'm using more information than TrueSkill uses, but it just shows that this might not be that bad. And I believe that Dr. Herbeck and Grapel mentioned that in these matches, the theoretical amount of accuracy you can get in a single match can be as low as 50% anyway. So here's some ways of using this information. So now that we have real-time rating information from match to match, we can use it obviously to rank the players. We can use it to improve map design, improve game design. So we've got some information about the game itself. We can use it to help players choose servers. And in fact, I put up there to auto-recommend servers. And I mentioned massively multiplayer online role-playing games. And because those type of games, these morphs, whatever, they manually build in things into the game that give players a natural progression, and players love that. They like having this kind of progression that they see themselves getting better and better. And it takes a lot of work and money and investment to do that for these players. Whereas if we have a system like this that figures out which servers are hardest, we can automatically recommend to a player where to go play. We can look at a player's rating and say, you know what, you should be playing here now. And as that player gets better, we can say, you know, you can go play here now. And so he can see himself progressing and kind of leveling up as he plays on the harder and harder servers. Another thing I can use these ratings and ranking systems for something I call passive team balancing. So in this, when a player jumps on a server, he wants to pick his team, I can go ahead and predict if he joins that team, how likely is that team to win? And if it's not acceptable, I can say, you know what, you can't join that team, you better join the other team, because you're going to make it unfair. And then I have something I also call active team balancing. So public server dynamics, because players are coming and going, switching teams, it means we have to balance during play. Players don't usually like this, but if we don't do it, then the gameplay will remain unfair. And so I have this greedy, right now it's just a greedy method, there are better ways we could do this. What we do is we look through and predict, kind of a one look ahead, that what would the teams look like if we moved this player over to that team, and we do that for every player. And then we move the player that brings the probability of winning closest to 50-50. Just kind of a greedy approach. This is, of course, uncomfortable for the player that's moved, but it increases the fun factor overall. Usually it's only 1 or 2 players moved per match. But another nice thing about team balancing that's also been mentioned in TrueSkill is that it's an example of kind of sequential optimal design. So the very act of making these games more fun for the players is also giving the adapting algorithm the most information. And for me, this is very similar to kind of what we call active learning and machine learning, where now I have this naturally adaptive system that can not only learn which players are the best, but it can learn which questions to ask. If you give it 2 teams, it's going to say, you know what, arrange the teams like this. That's the question I want to ask as a learner. If we think of the ranking algorithm as a learner, and then it can get the most information out of that game that it can get, which I think is interesting in general for machine learning.
But is that the objective? I mean, the objective is surely to have the best games and not to have the most informed ranking system.
Well, the thing is that those 2 objectives are kind of the same, because so the most challenging games are where you can have like a 50-50 kind of situation. It turns out 50-50 kind of situations also give the most information to the learning algorithm. So you think the biggest updates in the learning algorithm actually happen when something like a team that's 10% likely to win beats a 90% likely to win. Those result in the largest updates, but they also don't happen very often. So the 50-50 ones happen, 50% of the time. So if you can make every match a 50-50 situation, the hope is that you'll have a very fair game, and you'll also give the most information to the learning algorithm. And it's, yeah, it means you can, it's nice to have that kind of the fact that they both want to do that. So some future directions to take with this. I'm kind of interested in explicitly modeling these time varying changes instead of just taking for granted that the recursive updating method can track changing player ratings. I'd rather kind of do what Glickman did. And so Mark Glickman, he actually has some models, and they're single player models, not multiplayer like these are, where he explicitly models how player abilities can change over time. I think it'd be nice to see how that compares. I'm interested in looking at how the number of players affects a map rating, because recently I've noticed that there are some maps that players play on that if you're on a full server are a lot harder than if you're not. Just regardless of who plays, if you have 4-on-4, it's always easier for this, say, the Allies team to win. But if it's 16-on-16, which is still fair, it's way harder. And it's because you have things like better coverage on the defense side. And so I think I can get some more information out of that. Something I can use this recursive Newton-Raphson method for is kind of an online or an incremental version of Bayesian neural network training, which is nice. Yeah. And I also would like to try out expectation propagation because it seems so cool, I guess. I've heard some good things about it. And then I also like to do some direct comparisons to TrueSkill now that I have their data and a little bit more knowledge of their methods. Now, before questions, if we have time, I can kind of show you what these rankings look like. So I got this up about 2 weeks ago. This is kind of showing, we're getting close to 30,000 players, which is, I don't know, nowhere near as large as Xbox Live. It's still a beta though. 36 servers, these are the number of games we've seen. Now what I've got here is something called PR win percentage. It's a win percentage that I use the player ratings to compute. So I said there's different ways of ranking the players besides just taking a few standard deviations below their rating. Instead, I was trying to figure out a way of coming up with some way of ranking them that makes more sense to the players than just a strange rating number, like your rating is 1.3. So instead what I have here is I take their rating and their variance, and I put them on a simulated team with 19 other players, 9 on their team, 10 on the other team. And all these players I assume are average players and that have the same variance of that player. And then I just predict who's going to win. And so I get this. So these top players here, basically if they play in a game with average players, it's very unlikely they won't win, which is what you'd hope from the top players. I did some similar things to not as much success as far as readability with these other ones, but so here I'm ranking the map fairnesses. And this is I call the allied win percentage, which is a similar thing I do with the maps. And the nice thing is this top map right here is a symmetrical map. It's exactly the same for both sides, so it's good. It makes me feel good about the system to see it as being ranked as the most fair map. And then we can look at servers. So servers, I have this thing called the 9/11 win percentage, which basically says if we're playing in a game of 9 versus 11, how likely is it that the 9 will win? Servers where the 9 have a good chance of winning, that suggests that the skill is more important on the server than just having more players, which suggests that the level of gameplay on those servers is more difficult. Those are still kind of in the heuristic stage as far as yeah, it's just something that gives the players something they can understand a little better than the ratings. And that's it. Any more questions?
Well, thanks, Peter.
The question is probably outside of the work you're looking at, and you commented that active team balancing is going to be a strange gaming experience. You suddenly get thrown on the other side.
Yeah.
Have you explored opportunities for tuning the game parameters itself? You could imagine making things harder for a team that has an advantage to being overbalanced. You can slow down their movement rates, or half the ammunition can turn out to be duds.
Yeah. So
that would be something you can reflect back straight in the game experience itself. Yeah, standstill and suddenly appears you can't see anything.
That is kind of a cool idea, because so if I threw in the model something like speed.
Yeah.
And say what's your rating based on your speed? If I did some kind of regression there, that would be cool. The only thing I have that's kind of like that now is number of players per team. So as we are now, we try to find the teams that are most balanced in numbers as well as skill. But before we had that, we had some very interesting situations where the greedy algorithm would say, you know what, these players are so good, we're going to make it like 5 on 20. And so that's how it would do that. It would just basically figure out that if we throw a ton of players on that team, then they'll have a stronger likelihood of winning. The players hate that because then you have a team of 20 just looking for the 5. Yeah. And it's not very comfortable, and the 5 can never win almost in that situation. But yeah, that would be interesting to kind of model some of those other situations and handicap the team based on that.
So that's what I needed, handicap. Thank you.
Yeah, that would be fun.
Do you have any more thoughts about modelling how people's skill will change over time? Because, I mean, when you had that server 2, I think it seemed your model wasn't predicting very well on that server because you said it had a lot of beginners on it. So obviously these are people whose skill will change quite rapidly over time.
Right.
It seems that it's not just trivial to, it's kind of a complicated process of how that's going to happen.
Yeah, and the way I'm handling that right now is just I am hoping that the fact that now I'm ranking all the players together across multiple servers, that I'll catch their information as they move around. But so let's see. So Glickman suggested a way to do that, and it's been a while since I read his paper, but basically you can. So one simple way to do this is just to say, let's weight the effect of the games in the likelihood over time. So instead of my likelihood just being the product of all the likelihoods, it's going to be the product of some weight, like where t to the some value, where t is how far back does this game go. And then if I throw that in there, then I can account. It basically makes the more recent games count more for the players than the past games. And that's one way to kind of model the time range changes in just the player ratings, not in their variances, but in just their ratings. Yeah.
Any more questions?
Do you have some feedback on the perception that the users have on the way they are ranked? Like, do they understand why? Because the complex math going behind the scene. Do they kind of agree that it's relevant because I mean, this guy which has this very high ranking is really very very good? Do they?
They have. Do they tell me this player's good?
Yeah.
So yeah, let me show you. Not always, which is kind of sad, but so this second player right here, number 2 player, which taking to. Yeah, okay, so we look at this number 2 player named Bit. He's known to be a very, very fair player. And he's known to commonly join the teams that need the most help. And so when I see his rating up there, I kind of trust that. Whereas the top player, he's either a very, very good player as well, or he's very good at picking out teams that will win despite low ratings. He's a player that wants to win a lot. And the cool thing, though, about this, my goal when I first developed this system was to have players play to win. Before that, I had players that played to get the most kills or to plant the most dynamite, silly things that they would exploit. And so with this system, the players on our servers, they really play to win as their primary goal. So I have gotten some feedback like you're saying, and for the most part, these are very good players, but there's the occasional question is this guy just doing a really good job at choosing teams to win on, or is he really that great? Yeah. And that's kind of a concern, because we give them the freedom on a lot of these servers to make their own teams, and if they have the freedom, then it. Whereas in Xbox Live, you can prevent that a little bit more, which is kind of nice. Any more?
I've got a quick question. If you can go back to your slides.
Okay.
Actually, the one that's up right now. So you say it's an unfair comparison, but one question I would have is, if you look in your data, and if you look at the percentage of wins and losses without completely disregarding who played on which team.
Mm-hmm.
So what's that ratio? So the most naive way to predict the outcome is to just predict the majority outcome. So what's interesting is that it's the majority outcome at 65% or at 68%. Like, how much better do you get over just predicting the majority outcome?
So that I haven't measured. So you're saying just look at a player and see how often he wins, and then using that to...
No, look at the 300 matches you have.
Okay.
And see, on the 300 matches, how many are wins and how many are losses.
Oh, for say the allies side. Pick a side, you mean? Because there's going to be
independent side per server that would be.
Number.
If it's per server, you have 100 games. Do you have 100 per server?
Well, this one is 5,000, I think. But
I see. So you take per server and you just look at the ratio of winning and losing games. That'd be the most naive predictor of the outcome.
And then compare it to the...
And then compare it and see how much better you get over that number.
So that would so I have a baseline that's more fair, right? And then compare those. Yeah. I don't, but that's a good idea.
Okay.
That would be interesting to look at. Yeah.
And thank the speaker again.
Yeah, I think I'm free after lunch. Yeah. Well, we're having lunch with Ken, aren't we? So, yeah, probably make it. What time are we going after 12, aren't we? I think. Yeah. So, should be back certainly by 2, I hope.
Okay. I'll be around.
That was a celebratory move. It's my 30th wedding anniversary today.
We should be celebrating for that.
Yeah, maybe it's part of the recipe for success. Yeah, we should be back by 2.